So welcome to my talk, Recursive SQL for Data Mining. And the idea behind is, how does it look like in database machine learning? So the problem is we have a fully automated data pipeline that collects and processes all the information we need. But actually, it is a giant house of cards built from random scripts. So what is the solution to solve this problem? And the solution, in my opinion, is SQL. Because SQL is sufficient for machine learning as it is Turing complete with recursive tables. So the idea is that we can do the data preprocessing using SQL, so we do not have the need for data extraction out of a database system anymore. The structure of this talk is as follows. I will show you how clustering, graph analysis, and association rule mining works using recursive SQL. And then I will show you the evaluation. So let's start with k-means. So for example, you should know we have created some table operators and a hyper-inside web interface where we can execute all the SQL functions and also our recursive tables. So let's start by k-means, a clustering algorithms that clusters points, for example, airport data like this. So we have n-dimensional points and we want to cluster them to k groups. And what do we need? We need the Euclidean distance, and then we do a ranking. So a point belongs to the closest located point here, to the closest located clusters. So we have the initial case, which is just finding 5 clusters, and then we iterate until the cluster assignment doesn't change anymore. The second algorithm we have implemented is the B-scan. And the B-scan is a density-based clustering algorithm, so it does not have some fixed amounts of clusters. So here we can see Europe, and we see that it clusters Africa and Europe as one cluster, so as separate clusters, and not based on some initial clusters. So how this works, we have a maximal distance between 2 points, and we have a minimal number of points per clusters. Otherwise, a point is declared as noise. And then we have to look for every cluster whether there's another point whose distance is less than this epsilon away. And we can do this with some recursive table, So first, every point forms its own cluster, and then all the points get merged that are less than epsilon. So here epsilon is 1.5 away. And then as cluster ID, we just use the first, the idea of the first point. The next algorithm I want to show is PageRank. So we all know it from Google because it's how some nodes are ranked, for example, web pages. And how does this work? We have some initial value. So the initial value is, in our case, just the number of all nodes we have. So 1 divided through the number of all nodes. And then in each iteration, we distribute the PageRank value of a node to all outgoing edges. So here we have the initial value, and here we have the alpha for a stamping factor. And then the new PageRank value is just the sum of all incoming edges. So here's the formula, and here on the right, we see the equation in SQL. So the base case computes the initial PageRank, and the recursive step divides each node's PageRank value by the number of outgoing edges. And then it assigns and sums up the fraction for each destination node. So here we should see a sum. Here it's the sum B, and this is just the fraction for each destination node. Last but not least, I will show you the a priori algorithm. It's for association rule mining. So here we have some precondition and some postcondition, and we also see the support in how many item sets this item set is included, and we see a confidence, so how confident we can be for this association rule that flights who goes to Munich also goes to Zurich. And how does this work? We have a recursively growing relation. So we start by the one item set. So we have used arrays in SQL, and then we extend them in each recursive step until no more frequent item set is found. And now let's evaluate this. So what do we compare? So we have written the algorithms first in hyperscript, and we compare the performance of hyperscript operators to table operators in Hyper and MATLAB, and our now presented recursive tables. And as systems, we compare PostgreSQL to Umbra and Hyper. So let's first show k-means. So we have 10 to the power of 6 points. And what we can see, of course, the runtime occurs linearly with the input size. And what we can see here, the integrated operators perform the best, but also our hyperscript and recursive tables perform quite well, better than PostgreSQL and MATLAB. And what you can also see is that it performs faster with each additional core, but actually our operators are better implemented. Also, k-means, we can also see the same performance, like our recursive computation performs the same as our, here we see the recursive computation, and also our operators, they perform the best, and the scripting languages performs the worst. For the a priori algorithms, we have created some synthetically shopping carts, synthetically generated shopping carts, and we vary the number of items per shopping cart between 0 and 10. And what for measurements, we vary the support. So the higher the support is, the less frequent item sets exist, because support of 100% means that one item set to be considered as frequent must be part of every shopping cart. And what we can see here is that the operator performs the best. Also, the MATLAB function performs quite well, but also our hyperscript function using a recursive table performs badly. And the reason is that in our implementation in Hyper, it uses an honest operator for the arrays, and this needs quite a lot of runtime. Last but not least, I will show you the performance of the PageRank computation. So the PageRank was computed for 10 to the power of 5 nodes. And what we can see here is that our operator, as well as our recursive variant, performs quite well, and it outperforms the MATLAB operator and the recursive version in PostgreSQL and procedural language in PostgreSQL. The reason for this is that PostgreSQL is slower than our main memory database, but what we can see is that also recursive computation in PostgreSQL performs quite well compared to procedural language constructs. And we can also see that the scalability is not that good. Yeah. To conclude, I have shown you some data mining algorithms in SQL 92, just relying on recursive CTEs. And I have shown you 4 algorithms. So k-means, DB-scan, a priori, and PageRank in SQL. And what we could see is that the performance was worse than the operators in Hyper, but similar to MATLAB's library functions. And within recursive tables, what is necessary, we need the support of aggregate and window functions to fully use the possibility of SQL 92 and recursive tables. And by that, I thank you for your attention, and I am happy to answer your questions.